All right, hey people. Hi everybody. Hi Dr. Hibbert. All right, well we're gonna now move on to lesson 1.4 of Calculus 1. I got the right. Lesson 1.4, there we go. And here we're gonna learn about continuity and one-sided limits. Continuity, cool word, and one-sided limits, not two-sided. One-sided limits. I'm gonna put an exclamation point to show how excited. Two of them actually, not three, but two. All right, I'm gonna try to do this quick, and I won't try to be too theoretical and get straight to the point of how you can solve these problems because I actually don't find this stuff pretty interesting, and high school kids want to get those problems correct and know the math instead of oh, I know the proof, but yeah, don't tell other teachers that. But I know exactly what types of problems you're going to have on your exams and on tests. So here we go. So 3 types of discontinuities that you want to understand by looking at a graph. So let's look at them from what I draw here. What the? I need to work on this. Come on. I blame gravity. Try to make one big graph so that we can put all the types on one of them. Probably not. Where's my red marker? Okay, so when we have like a whole or removable discontinuity. So let's say we have some function going from like this, from A to B, and let's say it's C, which is between A and B. We have a whole. Remember that guy from the previous lesson? We have a whole. That's where the word whole got invented, from graph. Now, what does that mean? That means that you can't continue on this path. If you're driving, all the way to Vegas and you get to here, and you're like, fudge, there's a hole in the ground. You can't drive anymore. You can't just jump over it. You don't got that type of technology because it's a black hole. It looks white, but it's insane to the different universe. So the point of discontinuity is discontinuous. It doesn't continue anymore. And we say, essentially, this is a removable discontinuity. Removable discontinuity. I don't know why I wrote that bad. Why I wrote this big? Because it's a big deal. Removable discontinuity. Let's erase this hole. Let's make a hole like there. Discontinuity. Now, think of it as you just grabbed it and pulled it out. Grab it and you pull that crap out of the whiteboard. Because this is what's going to happen when you factor something. When you have a graph or an equation and you have 2 common factors. I mean, I could show you one, but let's say you have. Let me just make one up. X plus 3 times x plus 1 over x plus 1. Then this goes away, and remember how the graphs are of this and the one where these are canceled out are essentially the same, except for there's a hole on one of them. But I will go over some examples that are official and explain them and show them more clearly. But on to the next one. The next one. Should I start this? Let me just erase this. I don't like my handwriting. That's why it's a video. You can go back and you can go back and never come forward, never come back. What am I saying? Okay, so the next one is a jump discontinuity. These are the cool ones. So it's you're going along this path, but you're over here at A, and let's forget about this. We stop over here, and kabang, we start up down here. So these are both at C. These both have x values of C. This is a filled in circle. Filled in, so it's defined for C. This is the hole. whole not defined or undefined at C. Undefined for C. Because they both can't be defined, otherwise they wouldn't be a function because you have two values with the same x value, or two y values with the same x value. Okay. Now we call it a jump because just think of like, think if you're like driving to Y, and then you get to this cliff, and you're like, oh damn, this is a big drop. But since you want to go to Hawaii and party, you're willing to take that drop and go down to here. But you end up failing and dying, so it doesn't work out. But it's like a jump. I mean, this is one hell of a jump, depending on how far it is. Jump discontinuity. Jump discontinuity. Only the brave jump, and everyone dies when they do it. But it's true, dropping off the cliff. You can go up to, doesn't matter the direction, but it just matters that there's like a gap between them. All right. Oh yeah, and then let's mention that. So here we say that the limit of f of x, or the limit of f of c, it's not going to exist. What the heck? Okay, there we go. So the limit, remember, this is a function of x, the limit of f of x, as x approaches c, maybe you can say equals, but does not exist. So this function is f of x, but since you're approaching c from over here on this side, you would get to this value. Let's just say that's c comma 10, and then this is c comma 3. See, you're not going to be hitting the same point when you're coming from this side or that side. You're going to be like, hey man, we're supposed to hang out, but why are you way up there and I'm like, a cloud and I'm down here? It's like, that's all right, man, I'm coming, I'm going to drop. But gravity's too powerful and kills them. But it's not going to have a limit that's defined, does not exist, because both sides don't collide into each other. And the last type is where you have a hole, but the limit does exist. I'm erasing this. I need to clean my whiteboards. But I can't afford whiteboard cleaner, so I'll take donations, and I have to then of course pay someone to clean them, and they're expensive. But I'll take donations. So let's see what we'll do. Cool. What's it be over here again? A, B. And what we're going to do is start over here. We're going to go. And then C, you have a hole. And let's say this is C comma 10. Or this is C comma 9. Is this point right there. But you have another value here. C comma 2. You see? So then, for this case, the limit of f of x as x approaches c is equal to 9. It does exist because when you're traveling along this cool path from the left, you go to here, and when you're traveling from the right, you also go to there. So they meet together, bang, and then they're good. They're friends again. They're probably stopping at Panda Express, for some good food. Yeah. Now, one thing you want to know is that this is f of c. So if you were asked f of c, where does f of c equal to? That's not 9. F of c is 2. So f of c is not equal to f, the limit of this. So not equal. Just be aware or remember that and understand that, because they're usually going to have a test question on that. I'm never gonna ask in such a weird abstract way with a graph that you never seen before. But the point is the same. Limit exists because they go to the same point, but the function of c is not equal to that limit. All right, that's really the main three cases. I'll just go through some graphs and talk about them, and share our feelings. First, some water. All right, let's see what we got. Discuss the continuity of each function. All right, we're gonna have a discussion. Oh, this is so exciting. Right, Odie? Yes. He's really excited, but you can't tell because he's stone cold with his emotions. You can feel his emotions, right? So the first one we're gonna use, we're gonna go over f of x equals 1 over x. Which one is the f of x equals 1 over x. The next one we'll have for b we'll have f of x will be x squared minus 1 over x minus 1 over x minus 1. And for c, forget all these, we'll have a piecewise function, so f of x will be x plus 1 when x is less than or equal to 0. Whoa. That's on 0. Come on. And the other side will be x squared plus 1 when x is greater than 0. X squared plus 1 when x is greater than 0. Let's go with that. Okay, so now, what does this graph look like, guys? Wow, it's obviously going to be, let me get back to you. I'm looking at my notes right before. But you should just know, because you've done that so much, you're going to have the hyperbola. Actually, no. Well, yeah, you will actually. But it's going to be undefined when x is 0, so along the y-axis. So you're going to be having something like this. Remember? 1, 1. And negative 1, negative 1. So then what's going on with this graph? It's, cool looking, but the main thing you want to understand about the continuity of the graph and how limits can play a role. Now, it's discontinuous for x equals 0. Discontinuous at x equals 0. But how is it discontinuous? Is it like a hole? Is it a jump? Is it like the other type where we're like that's really it. Is it like doing something crazy? Like what is it doing? Like is it going to infinity, negative infinity? Is it approaching a number? But for now, really just understand if it's a removable or non-removable. Meaning that if it's a removable, it's really just a hole that you can pull out. Here you can't really do that because it's going to infinity and negative infinity, Like there's too many. It goes through the roof and to Mars. So non-removable discontinuity. Non-removable. Now you can also use the equation to recognize this because we can't change this to make it another equation that's very similar. Because if we were able to remove it, we can make another equation just like this, except it would just have a hole at that value, but it can't. So that's all. Non-removable. That's what they're going to look for. Now, the next one. All right. Now, this may surprise you. This graph will actually be a straight line. Because remember, you can. Let me draw an arrow down here and rewrite it as. Let's say g of x would be, it's how can be factored into x minus 1 times x plus 1, right? That's right. but then you can factor out an x minus 1. So g of x is just equal to x plus 1, right? That's right. And so you're just graphing this line, essentially. X plus 1 goes through 1, 0. Negative 1, 0. You better know that. You definitely should know this. If you don't, you're screwed. And I can't help you until you know this. So yeah, you should give up. No, don't give up, but you're kind of screwed if you don't know how to graph this line. At least for the time being. How's that for motivation? Well, too bad I'm not a motivation speaker, I'm not a teacher. But anyways, here's my invincible ruler. I love rulers. Don't take them for granted. Now we have that line. So this is g of x, but we want f of x. So this is undefined at 1. Because if you plug in 1, you'll get 0. So this point would be a hole for f of x. If this is f of x has a hole at 1, 0. Now, this is removable because that's what we did when we factored out. We got rid of it. Hooray. So, removable discontinuity. Removable discontinuity. Discontinuity. Yay. And you have to write it like that, otherwise, stuff is going to happen. I'm just joking. All right, C. Now, this is kind of a trick one. I wish I had picked a different one, but if you were to graph this, and for these things, if you are kind of rusty or take a long time to figure out what the graphs look like, just use a graphing calculator because that's not the point right here. The point is to understand the graph. So this would be a straight line up to 0. And after that, it'll be a parabola. So 2, 5, right? That sort of thing. Yeah. Now, it's continuous everywhere. That's what we say. It's continuous everywhere because there's no jumps, holes, issues. It's defined for any value you plug in there. All right. Do I have to write it there? Continuous everywhere. Because I like saying continuous everywhere. And for this occasion, I'll use purple. Nice. Continuous. Continuous everywhere. You want to see what passion is. Continuous everywhere. Even in your careers. Exclamation mark. All right, one more. Then we can get to out of here and to your math, back to your lives. Let's look at the sine function. That one's continuous everywhere too. Let's look at another one. Let's look at a one-sided limit. I want to find a really good one that's gonna, make you be like, wow, that's fucking amazing. I wish the video kept on going forever. Can't find a good one though. Sorry, just talk amongst yourselves. Okay, so let's look at the tangent function actually, because then you can see how do you describe it, because it's continuous, or it's defined for every value, but it's not continuous. Right? That's right. Put some muscle on it. Should I have very little on? All right, so let's go and write y equals the tangent of x. Famous tangent function. It's always more popular than all the other trig functions. It gets all the attention, gets all the chicks, and all the other functions are jealous because it can't help itself. Okay, so then the tangent function, remember, is equal to the sine of x over the cosine of x. So anytime the denominator or the cosine of x is equal to 0, this is going to be undefined. So it's undefined for pi over 2 3 pi over 2 5 pi over 2 and so forth. 5 pi over 2 and so forth. And it goes the other way too. Don't mind that it's crooked, it's just your screen that's crooked. So negative pi over 2. And yeah, let's keep on doing that forever until you run out of space. But it'll still keep on going, negative 3 pi over 2. Now, so it's defined for everything, but it's not continuous because it has these crazy asymptotes. Where's another marker? And I always struggle to draw these curves perfectly. I'm gonna try, concentrate. Let's do purple. Here we are. All right, here we go. All right, come on. It's all about the smoothness. Can I get good form? All right, here we go. That's it. Okay, it's not bad for now. And go like this. Start drawing the scale and go and so forth. Go yeah. So it does this over and over. But again, it's defined for every value. Well, did I say that wrong? Yeah, well, it's not defined for every value. Actually, I was saying that wrong. I was testing you. So it's not defined for multiples of pi over 2. And so it's discontinuous at multiples for pi over 2. So we can talk about how it's continuous on open intervals, but not continuous on closed intervals. So it just depends. So you may get a question that words it in one way or another, because again, these are asymptotes, but you can say it's defined or continuous, defined and continuous on the domain that we use. So we have negative 3 pi over 2, and we're going to go backwards like that. I think that's a thing. We're also going to go forwards. 3 pi over 2, negative pi over 2. Oh, well, actually, let me write it this way. So it's continuous on this interval. So negative 3 pi over 2, comma, negative pi over 2, skip, or you could put a union, comma, negative pi over 2 to positive pi over 2, skip or put a union. Okay. Pi over 2 to 3 pi over 2. Three pi over 2, and so forth, to 5 pi over 2. Yeah. I mean, and you could go the backwards or do plus minus, but that's the idea. So it's continuous on open intervals. These are open intervals because we have parentheses. So it's like a technical thing that you have to make sure you understand. If we put brackets around it or say closed intervals, it wouldn't work because it's not defined at these asymptotes. So it just depends on how you want to write it or how you've been learned or taught to write it. Is make sure you write it correctly. It's not continuous everywhere. It's not continuous for multiples of pi over 2, or it's continuous on open intervals like that. All right, so I'm gonna make a chapter 1 summary where I'm gonna do a bunch of practice problems that are pretty much the main ones that are gonna be on a test that your professor or teacher will give you, because those are gonna be like the ones I give on a test. Like obviously gonna give you the same ones, but ones that are like it. So keep an eye out for that. Let me know if you have any questions and comments, and feedback is always helpful. And thanks for watching, and subscribe and like and tell your friends, tell your mom. All right, bye.